Our next presenter is Emma Lord, PhD student from the Department of Chemical Engineering and Applied Chemistry, Faculty of Applied Science and Engineering, with the talk titled Sweating the Small Stuff, The Path to Cutting-Edge Zinc Batteries.
Don't sweat the small stuff. It's an idiom we've all been told. Today, I will demonstrate that when it comes to batteries, it is imperative that we do sweat the small stuff. Lithium batteries are everywhere. They are on our phones, medical devices, and personal laptops. They offer excellent performance. However, they have a dangerous tendency to catch on fire, are expensive, and are often sourced unethically. My solution? An innovative zinc battery, a safe, ethical, and cheaper alternative. The zinc battery is like a tiny jelly sandwich, a positive end, a negative end made of zinc metal, and a liquid, called the electrolyte, sandwiched in between them. The key determining factor of effective battery performance is the way that the liquid and the metal interact. Why is this so important? Microscopically, an ultra-thin layer, no thicker than a strand of hair, called the passive layer, forms from the chemical reactions between the electrolyte and the zinc. The passive layer can evolve in one of two ways. In a beneficial way, forming a durable protective layer, like in the top diagram, or in a destructive way, forming tree-like branches that snap off and short-circuit the cell, like in the bottom diagram. Although we know that the passive layer plays a central role, we don't quite understand how it forms. In my project, I work to uncover the mechanisms in which the passive layer forms to then help us engineer novel zinc batteries with enhanced performance. Simply put, I measure passive layer formation in two steps. First, I place droplets of our electrolyte on the zinc surface and see how the zinc reacts with the droplet. This is like putting jelly on the bread and seeing how well it spreads. The changes on the bread act like clues, giving us real-time insights into what is happening at the interface between the liquid and the metal. Second, using advanced microscopy, I determine the roughness of the passive layer, its chemical composition, and obtain high-precision visual images of the passive layer as it forms. By combining the droplet measurements with enhanced microscopy, I can identify specific zinc electrolyte reactions and pinpoint exactly how the passive layer develops over time. With these insights, we can develop a new generation of zinc batteries that are safer, ethical, and more affordable. Batteries that won't catch on fire and won't compromise on performance. So, if there's one key message that I hope you take away today, it's this. When it comes to innovation, the smallest details often matter the most. And sometimes, by sweating the small stuff, we can unlock the biggest breakthroughs. Thank you.